I'm David Hone, and welcome to another video episode of Engineering Design and Management Planning. I am sure you are all aware of the stress and strain which the majority of engineered structures go through on a daily basis, from roads withstanding the weight of cars to buildings enduring gale force winds. Today we will be covering the thrilling topic of elastic and plastic deformation, which relates heavily to the work behind selecting appropriate materials for specific jobs and the methods in which they are used. Now, you might be wondering, what exactly is plastic and elastic deformation? Well, elastic and plastic deformation occur when a sufficient load or unaxile force is applied to a metal or other structural material, causing the material to change shape. Elastic deformation involves the stretching of bonds within a material as a result of an unaxile force being applied to it. However, not to a magnitude where they are forced to slip out of place. Elastic cases see the object self-reverse the effects of the force on itself once it's removed, returning back to its original shape, showing no noticeable characteristics of a force previously being applied. Plastic deformation, however, involves the dislocation of these bonds as a result of the unaxile force. The object will show signs of the force exceeding the material's elastic threshold by obvious changes in both size and geometry. Elastic deformation can be both linear and nonlinear. Materials such as rubber, concrete, and neoprene have a nonlinear relationship with deformation as a result of their high elastic deformation ranges. Materials such as crystals, most normal metals, and the majority of ceramics, however, have a linear elastic range, which is much smaller than that of the elastomers. The linear elastic deformation relationship can be shown by Hooke's law. Hooke's law is the law stating that the stress on a solid substance is directly proportional to the strain produced, provided the stress is less than the elastic limit of the substance. As stated in the definition, Hooke's law only applies to the point where elastic deformation ends, which is the same point where the material is at its yield strength, or the beginning of plastic deformation. All materials must undergo elastic deformation before plastic deformation. However, it all depends on how tolerant the material is to strain as to how much force is required for a material to pass its elastic deformation stage. Materials such as gold, silver, and copper have a large plastic deformation range. However, they have very poor elastic deformation ranges. This means that, as shown in the graph, the elastic stage is passed very quickly, meaning that it has permanent damage to its shape. However, these materials, once in plastic deformation stage, can be easily bent and worked into their desired shape. This is one of the reasons that these materials and other forms of ductile metals are used so regularly in engineering and everyday applications, such as piping, furniture, cars, and even jewelry. Despite some materials being workable in the plastic deformation stage, the material will arise at a point where it cannot possibly take any more strain. At this point, the material will fracture and see all of the atoms completely split from each other. This process is irreversible, and for some materials such as crystals and rubber, occurs very shortly after plastic deformation. It is very important when considering materials for engineering applications to consider the characteristics of the materials in regards to elastic and plastic deformation. Uninformed choices of the materials could see disastrous results if the stress and strain of the material isn't considered for a particular application. To ensure that you don't get caught out choosing the wrong material for the application, make sure that you do your research on the material before it is used somewhere that it shouldn't be. This has been another video episode of Engineering Design and Management Planning with David Hone.